Welcome to another video on the Moving AI web channel or YouTube channel, and today I'm going to give a talk from AAAI 2025. So this will basically be the talk that I gave at the conference there, but of course I do get to give it a little bit more slowly there. It was a 15-minute talk. I'm sure it'll take a little bit longer here. This talk was work done with my master's student, or my former master's student, Mohammed Reza Hami, at the University of Alberta, and we're going to be talking about how to do suboptimal search with dynamic distribution of suboptimality. In this talk, I'm actually going to spend probably more than half of the time trying to motivate what we're going to try and do here. Because once you understand that, then the rest of the details are a little bit easier to understand. We're not going to get into the really technical details here, but the goal here is to give a high-level view of this new idea of how we can dynamically make some decisions at runtime in algorithms similar to A*, weighted A*. And so let's get started and see what we can do today. So what do we have here? So I want to start out with just a basic picture of A*. Okay, so this is normally how we'd be watching A* run. If you've seen my demos before, then you might be used to seeing this sort of thing on some of my demos and on those pages. And what we're doing is we have a start state, which is going to be somewhere down on the bottom. Now, this is actually, I'm drawing it large so you can see it really clearly here. The goal state is up at the top. The actual state, so these are room maps. So there's like 16 by 16 rooms, and then every state is sort of one small cell here, is much smaller than the large boxes that are drawn here, which are there more for visibility purposes. Okay, but we have the start at the bottom, the goal at the top, and we're going to do a search. And here in red, we're drawing the closed list, and green is the open list. And then when we're done, we find the optimal path with A*. That path is represented in blue. And so this should be a fairly standard picture that many people can understand for how like A* works and how you see it on a map, solving a particular problem. But I want to introduce here another way of looking at this problem, which for those of you who might be familiar with some of my content here, it may be familiar, but for many others it's not. And here what we're going to do, so on the left-hand side we have the normal, which is a map embedding on these xy coordinates that come from the map. On the right-hand side, what we're going to plot is the g and h value. So every state that we expand on the left-hand side is going to be plotted on the right-hand side by its g and h value. And remember, A* is prioritized by an f value, which is g plus h. So if we run this here, what we see is every node on the closed list is red on the left side, it's red on the right-hand side, except instead of plotting its x and y coordinate here, what we're plotting is the g and h value of each state on the right-hand side. So that says where any particular state is going to be. The green states are on the open list, and the red on the closed. Okay, and what we see under this view is one additional thing here, which is this blue line. And to understand this blue line, what we want to think about is, what is this equation f equals g plus h? And the answer to that is actually that this is it's an equation of three variables. And so we have g and h, and then we have f. And so on the plot on the right, we've plotted g and h, and we can think of f, the priority, as actually what we're getting is a three-dimensional surface out of this f equals g plus h. And so, for any g and h, then we've got this height of a state we could think about as being the f cost of that state. Now, the issue is that if I were to plot these surfaces, and we've tried them, they're actually really hard to visualize, and they're really hard to understand. So instead of visualizing the entire surface of states and what the priority function looks like on the right-hand side, what we draw is we draw isolines. And so this is a set of states that all have the same f cost. And so this is, you could imagine sort of like a mountain, right? You walk along and you'd all be at the same elevation. So along these lines, all the states have the same f cost. And this hopefully is clear because g plus h is constant. So if g and h are equal, then we end up in the middle. Here, if g is 0, then we end up in the bottom right-hand corner. And if h is 0, then we end in the upper left-hand corner, and there's just a linear interpolation between those, so we get this straight line. Okay. Now, the question is, well, what does that actually mean? And to continue to understand this, let's look at weighted A star. So weighted A star, the change that we're going to use here is f equals g plus w times h. So we're going to weight the heuristic, and you may be aware that when I weight the heuristic by w, I'm going to find a solution that's at most w times suboptimal. So if we now do this exact same problem, we plot it on both sides here, what we see is our line that was horizontal before, or that was diagonal before, with a slope. It's a slope of -1. In this talk, I'm going to negate the negatives, so it's a slope of 1. Here, what we've done is we've actually we've got a higher slope, so we essentially have a slope of 2 here. Again, -2, but it's a slope of 2 for our purposes. And what this represents, actually, the slope is representing the suboptimality. And so what this is saying, for instance, is that I have equal preference for a state with, for instance, a heuristic of 10 versus a solution with a g cost of 20. And so I'm willing to take a solution which is 2 times, if w is equal to 2, that is like 2 times suboptimal, where h is sort of the minimum bound. Again, sorry, as a reminder here, if you're not familiar with heuristic search, g is the cost for the estimated cost from the start to the state. H is the estimated cost from this state to the goal. In A star, when we are finding optimal paths, then G is exactly the optimal path. In weighted A star, it's the estimated path, or it's a bound on the path, or we get a bound from it. Okay, so let's continue here, and let's look at another example. So we can have this priority function on the right gives us this the surface on the right-hand side, which has these isolines, which are just diagonal lines. But we can do some other really interesting things here, right? So we can do this, which is called XDP, is a convex downward parabola. This is from a 2019 paper. And the equation is a little bit crazy here. But in practice, what it's doing is we see that we've taken our isoline, and instead of having a straight line, we can have a curved line. And there's a whole theory about what can be done here, and you can find some information about that elsewhere on my webpage. But if we look at this curved line here, then we can ask this question, well, what does it mean when I go from weighted A star, which has this straight line going across the state space with a slope of 2, where now I have XDP that has this sloped line. And what's interesting here, or I just want to point out, is the point that it crosses this x, or the h-axis, and the point which it crosses the g-axis. When I have a weight of 2 on my problem, then those 2 points are always going to be related to each other by this weight that I get. And we'll mention that again in the next slide. In fact, let's go right there. So globally, we're going to have a suboptimality of W. But what we're going to do is we're going to plot, we're going to run the same problem again, but we're going to plot on the left-hand side, instead of the open and closed list, we're going to plot the local suboptimality that we're able to have at this portion of the search. Okay, and this is going to go anywhere from 1, meaning that we have to be optimal, to 2W minus 1, meaning that in that portion of the state space, I can be almost twice suboptimal, so 2W minus 1. And so if we run this, what we see, what XDP is doing, is on the left-hand side, the blue states are the ones that are most optimal, and the red states are the ones that are most suboptimal. And so what XDP is, it's smoothly interpolating from the start to the goal, or from the beginning to the end of the search, saying we're going to be optimal at the beginning, and we can be highly suboptimal, 2W minus 1 at the end. Okay, so it's interesting then what the geometric interpretation of this plot on the right is that the slope of this line dictates how suboptimal I can be locally in one portion of my state space. Okay, and as I search across my state space, I'm able to be suboptimal in different ways in different parts of the state space. Okay, and so we can now go back and we can say, well, what if we go back to weighted A star, f equals g plus h, and we plot what's going on here. And what we see is that weighted A star was always saying I can have the same suboptimality, or I must have the same suboptimality everywhere in my state space. And so it can't be more suboptimal in one place and less suboptimal somewhere else. But if we use one of these other priority functions, we could do that. So I'll show you another priority function. This is piecewise xt. It says if g is less than h, then I'm going to essentially run a star because my priority is going to be g plus h. And if g is greater than or equal to h, then I'm going to get a normalizing constant, and then I get g plus 2w minus 1h. And so that is is essentially running weighted a star with a weight of 2w minus 1. Okay, and so my global suboptimality bound here is w, but locally I'm either going to be 1 suboptimal, or I'm going to be optimal running a star, or 2w minus 1. So as we run this, what we see is the beginning of the search has a weight of 1, the end of the search has a weight of 2w minus 1, and there's sort of a strong boundary between these two parts, and that's just because our priority function on the right-hand side is a piecewise function where the first piece is slope of 1, and the second piece is a slope of 2w minus 1. Okay, now let's look at an analysis of what we like from our priority function. And what we see here, so we're going to go to a new domain. This is a map with random obstacles in it. We'll explain what's going on the right-hand side in a few minutes. But we've got this random obstacles, and we have this region which is in blue, which is more expensive for the search to go through. And so we want to analyze what happens with these different priority functions as we try to search through this region. So the first thing we're going to do is we're going to just keep running piecewise xt here. And so let's run piecewise xt, and let's search from the bottom of the map to the top of the map. And what we see in this problem is that on the bottom of the map, as it starts to go up, then we are running, and this is the green dots here, so we're actually defining this region is a weight of 1, and so we run optimally through this part of the state space, and then we get a weight of 2w minus 1, and we run suboptimally through this weighted region of the state space. And so that's going to work really well in terms of getting through this weighted region that's expensive because I don't have to pay the cost of, or when I come to this expensive region, what happens is that I'm able to use this high suboptimality to push right through that expensive region, and then that makes the search really efficient. But alternatively, what I could do is I could search the other direction. So exact same problem, we're just going to search the other direction. And now we're trying to be optimal first and then switch to suboptimal. And what we see is we pay this huge amount of work because we're trying to find the shortest path. And this blue region's really expensive. So the search says, well, maybe there's some other place I can go to find a less expensive path through this area. So let's keep searching and searching and searching. We don't find it, so eventually we just use this high weight to go through here. But what we'd really like to have in a problem like this is we'd really like to see that if I start at the top, then I'm going to put this region where I can be suboptimal right here in the weighted region, so I can use it immediately. And if I search the other direction, searching the other direction, I would not use up my suboptimality, and I'd save it to be able to use it in case I run into the need for it later. So this is the algorithm that we're going to propose here, and it's based on this understanding that we can change our suboptimality. So let's get into how this algorithm then actually works. Okay. So what we're going to do, this is going to be called Dynamic Suboptimality Weighted A star. And the idea is we're going to divide the priority function in two parts. So this is our G and H axis here. And at runtime, we're going to choose what I want my suboptimality to be in any given part of the state space. Okay, and so let me show this picture. I'm going to turn off my camera here just so I can show the animations a bit more clearly. But so we've gone here, and the first thing that we're going to notice is that when I start, the start state has some H cost in the world, but has a G cost of 0. So the search always starts on the H axis, and it's making its way towards the G axis, because in the end of the search, I have some G cost, which is the cost of my solution that I found, and my H cost is 0 at the goal, by definition, at least with an admissible and consistent heuristic. So the first observation we make is that we have this property of our searches. On most problems, we can, of course, create adversarial problems that don't have this property. But on most problems, what we see is that our search, the states that we see in the search, they start on the H-axis when we plot their H and G cost, and they make their way incrementally towards the G-axis. And so there's a notion here that I can break my state space into rays, and I can actually, as I break it into rays, I don't have to define what the priority function looks like. until I get to a particular ray as I'm searching in my search. So what we're going to do is we're going to divide our state space into rays. We could have sort of an arbitrary number of rays in the state space. And on each of these rays, we're going to have an f cost, which is going to be some normalizing constant times g plus w of I times h. So this idea here is we're going to have this piecewise function. It's going to be each piece is going to be normalized to get a continuous and contiguous function from the h-axis to the g-axis. And then what I can do is I can choose between each of these rays what I want my weight to be for weighted A star. Okay, so now what we're going to do is we're going to look at this picture of how this happens, and we're going to show essentially what a human might do if we were trying to optimize this, and then we'll talk about how we could do it more automatically. Okay, so this is a picture. It's a screen capture from a video we're going to run in just a second, but we're going to try and unpack and understand what's going on here, and then we'll come back and we'll watch what's going on. So we've got our rays here. In this case, I've made them yellow and red. Eventually, I may add more rays, and I'll release this as a demo. But right now, for this talk, we just have 2 rays here. And by dragging these rays back and forth, so in the actual demo, they can be dragged up and down, and these points can be dragged up and down to describe this purple line here, which is what my priority function looks like. So this tells me at the beginning I'm going to be optimal, and then I'm going to have some higher suboptimality, and then I'm going to go to some medium level of suboptimality. So that's what these lines mean here. And at this point in this video, which we'll get to in a second, we've done some portion of the search from the start to the goal. So at this point, this line right here represents, I'm not showing all the individual states here. It'd get a little bit overwhelming if I did that, but I'm just going to show what is the state with a maximum slope here that I've expanded so far in terms of f and g. So as I do this work, I'm going to see this purple line move up. And if I want to avoid doing re-expansions in search, like either basically doing re-expansions or having to resort my open list, then what I need to do is that the states that I've already expanded, I need to have their priority function be absolutely fixed and never change again. But the states up here that I haven't seen, I haven't seen any states up here. There's nothing that prevents me from actually going and changing the priority function up here as long as it meets some theoretical requirements. I'm not going to talk about the theoretical requirements in this talk. If you go look at the paper, you'll find them there. Okay, so the notion is that down here, once I do some search, I have to fix the priority function, but above the search that I've done, I can set my priority function to be anything that I want. And so we're going to do this manually inside inside this video, because I didn't want to run a demo in the middle of my talk. Actually, I couldn't run a demo in the middle of my talk at AAAI. But let's go ahead and I'm going to narrate as we watch this video of this demo going on. Okay, so what's happening here is we're going to start, and we're just going to show that I can drag these lines, I can move them around, I can move these points up and down, and I can choose what I want my phi function to look like. But what I'm going to do now is I'm going to go on the left, and I'm going to start solving a problem. And I'm going to step that search incrementally. And as we step, we see here that the phi function that I have so far, the priority function has already been set. And now what I can do is I can change this priority function to be a little bit different. And when I change that priority function, I can then continue the search, and I can manually say that I want the priority to be higher in this middle region of the search. I apologize, this bar got here on top. Let me see if I can just go back. I'm going to show this one more time. So we are here. We can move around this function however we want. That is the purple line, describes my priority. And I can start doing the search. So here we go. We'll start the search. We'll drag the start and goal. We will step this one step at a time. And then what we're going to do is we're basically going to pause the search, and I'm going to reorient what the function looks like on the right-hand side. And I can do that as long as I don't change what it looks like underneath the line. Now I'm going to restart the search, and I get to use a really high priority because I got to the expensive region on the left-hand side. And this gets me right through this expensive region and allows me to reach the goal. Okay. So then the question is, this showed how I could do it manually because I could see the whole map, I could see when it got expensive, and I could change my priority. So if you have a domain like this where you have some costs that are not captured by the heuristic function. So some sort of dynamic cost. It might be from other agents that are moving through the world. It might be there's some sort of effect that's going on, like a crowd moving through, and you want to temporarily avoid that area. What we're going to do is we're just going to look here and say if the cost of some action divided by the heuristic of that same action is greater than 1, then there's some cost in my environment that I don't know about. And so what I'm going to do is, hey, there's some cost here. I'm going to use a high weight in order to try to move through that portion of the environment more quickly. And if it's the case that my heuristic actually exactly captures the cost, then I'm just going to gradually interpolate between 1 and 2w minus 1. It's sort of like running XDP, but it happens locally, starting from wherever I am in the search and working towards the end. There's other policies that we have in the paper and even in the code that we haven't, I'm not going to present here. But let's move forward from here and then see how this is working in practice. So what's happening is we're going to search from the top to the bottom. And we're going to run this really slow so we can watch it happening. And so here I go, I'm running the search. And what I have here in blue are each of these rays that I'm using to divide the state space. And so once I come into this blue region, then what I'm doing is these green dots are showing me what my priority curve looks like, my priority function looks like. And as I go through this red region, the blue region, then I'm upping the priority. And then when I come out of it, I'm going to lower the priority again. I have another video here. So this is running at like, I don't know, 8 frames a second or something like this. It's running quite slow so that we can see it and I can narrate it. And so we have to wait for just a second for it to start running here. But what we're going to see here is that we start running, and at the beginning we're just going to be, we're running with a very low priority. And then as I come to this expensive region, then I switch to this very high priority. In fact, in this case, I was going to do it anyway because I had a lot of suboptimality that was available to the algorithm, and I hadn't used it yet. And I think we're going to run one more example here. We'll have to wait just for a second to get it running. Yeah, here we go back the other direction. So here what we're going to see, and I'm going quite a bit farther back the other direction, I come to this region very early in the search. I'm going to use this high weight to get through the state space, through the expensive part of the state space. But once I get to the other side of here, right, then I'm turning and using a different suboptimality to finish the search. So this is another demo that will be on my webpage eventually. It's not on there right now, but once I get a few more things polished up, I'll make that available, and then you can play around to see what happens and how this dynamic weighting is enables me to solve some problems more efficiently. Now, we'll look at a number of different experimental results here. Actually, just 2 of them. There's a lot more in the paper, and Mohammad Reza had a lot more in his thesis as well. The first thing we're going to look at is the sliding tile puzzle. So it's just standard sliding tile puzzle. And on the x-axis here, actually, I relabeled this in the talk at AAAI, and I forgot to modify this version of the talk. But this is the weight. So we're just looking what happens as I use different weights with weighted A star, and this is the number of nodes that are expanded. And sliding tile puzzle grows exponentially, so we expect to see like this big increase. So this is a log scale over here. And what we see here is like piecewise XU is a really bad function on the sliding tile puzzle. XUP is similar to this. So these are ones that are highly suboptimal at the beginning and then try to be optimal at the end. There's a lot of algorithms that are really close to each other. In the end here, this is the dynamic weighted policy. It does pretty well, and this is the moving average policy. It does very well, but these algorithms are pretty close to each other. So it's something reasonable here, but some of this is coming actually not from it's not coming from the fact that we're being dynamic because the state space isn't dynamic. It's actually coming from the fact that the underlying curve is actually a pretty good priority function to use. And that's where we see XDP is pretty similar to this. It's also doing well. Okay, but if I take the sliding tile puzzle and I choose to weight some portion of the state space randomly in each problem, then what I suddenly see is this dynamic weighted algorithm is able to change these weights and very, very effectively, like an order of magnitude better than piecewise XD, even piecewise XU. So it does a very good job of finding solutions here and doing it very, very quickly because it is able to reason about what's going on in the state space and when it needs its suboptimality. Another example I want to show, because it illustrates some of the, it really illustrates a couple things about when this is going to be more or less effective as an algorithm, is on maze maps. So there's two things we see about maze maps that actually make it hard. And one of the things we see is that in a maze map, you can get a state that has a high G cost, has a very low H cost, but is actually very far from the goal. Because I can be on one side of the wall, the goal can be on the other side, but it's a maze to get there, and so I'm still quite far away. What that ends up doing is it causes me to define my entire priority function far before I actually get to the goal, and I lose this ability to be more dynamic in actually assigning my weights as I search through the state space. So this is a problem, and it comes from having a really weak heuristic. And the other thing we've seen, of course, is that if I have dynamic weights in the world, then like this dynamic weighted policy is able to really, really take advantage of that. So if we take our maze maps, we add a strong heuristic to it. In this case, we are doing 10 embeddings, 10 embeddings of a differential heuristic, and we add to it this dynamic cost region. Then we see the same thing we saw with the sliding tile puzzle, which is this dynamic weighted policy. Now, this is no longer a log scale. I don't believe it's a log scale here. If it is, we're zoomed in so much, it's not really making a huge difference. But so it's not like we're 10 times better, but we're a significant fraction better than all these other algorithms. Weighted A star is up here. Okay, there's a lot more that could be understood here, right? I'm already much longer than I was able to be at AAAI when I gave this talk, but let's just look at our general conclusions here, and I'll talk a little bit about this. So we'll run the same demo as before. So this is in this talk, we've introduced an algorithm, Dynamic Suboptimality Weighted A star, that divides our state space into, by these rays, into these individual regions, where in each of the regions, I can have a separate priority function, and I can use the properties of the state space to be able to decide at this part of the state space and this part of the search, should I be using a high weight or should I be using a low weight? And so this is something we've never seen before in algorithms like weighted A star. So this is something that could be powerful in some domains. What I want to say though is that, and this is a question that was asked, like, does this only work in the weighted domains? And the answer here is going to be that I need some sort of signal, right? If my domain has some sort of signal that I can take advantage of, then I'll be able to be very, very effective in practice. If it's completely random whether in one part of the state space I should be using a higher or lower weight, then the algorithm isn't going to be able to do a good job of making that decision. So this is something that you might, on a particular domain, even maybe think about using reinforcement learning or something like this to try and do a better job of deciding what it is about this domain that will allow me to decide to use suboptimality at this part of the search or some other part of the search. But as I said, this is the first time we've been able to think about this in terms of dynamically changing where I want to be weighted. And we already have some ideas in mind of where we might actually be able to apply this. And so I'd say, watch this space in, hopefully in a year from now, we'll have another paper that will describe some exciting new things that we could combine this together with. So we'll see. We, of course, haven't done that research yet, but I think there are some novel applications that could be used for this, at least some that I know of, and other people may have others that I don't know of. And so looking forward to see what people are able to do with this work. So thank you for your attention today. I hope you enjoyed this. Of course, if you have any questions, feel free to pop them in the comments. I'll be glad to answer any questions below. Thank you.